I welcome you all to this RILEM Technical Day for 2018. So just a few words about our first lecture. It's a very special lecture for RILEM and for us because it's the lecture given by the 2018 L'Hermite Medalist. And in RILEM we have 3 major awards that are attributed on scientific criteria. 2 of them are the L'Hermite medals, and they are attributed to researchers below the age of 35, and they are attributed during the spring meetings of RILEM. And we have the most prestigious award, the L'Hermite Award, that will be given today. So these awards are quite historical, at least for the L'Hermite medal. It has a long history of very famous names. And today we have the pleasure of having someone who is from the asphalt and bitumen community. And the cluster convener of asphalt and bitumen in RILEM made me notice the other day that it was the first time that we have someone from the asphalt and bitumen community. Although we had some amazing experts in RILEM, it's the first time the award is given to someone from this community. And it can be noted that today in the jury, this year in the jury of the medal, there was no one from the asphalt and bitumen community, so it was attributed by people from cement. So which tells a bit about our outstanding the academic production of the L'Hermite Medalist this year is. So I won't take more time. So my usual procedure for this medal awarding ceremony is that, okay, he was selected by the jury, but we still have to listen to his lecture. And if his lecture is good enough, then we will award him the medal for real, okay? So I count on you. If you don't applaud enough, or if you don't ask any questions at the end of the lecture, then maybe I will keep the medal for myself, all right? So, Fernando, the floor is yours.
Thank you very much, Nicolas. Good morning to everybody. And first of all, I would like to say thanks to the member of the jury of the L'Hermite Medal for giving to me this prestigious award. The title of my presentation is Designing More Durable Asphalt Material, and the structure will be divided into 4 different sections. As an introduction, we are going to talk about asphalt material design. Then, I'm going to tell you how I have tried to fill the gaps to obtain more durable asphalt material. After that, we are going to tell you about some of the experience carried out on this issue in the Laboratory of Construction Engineering of the University of Granada, where I work. And finally, as a conclusion, we are going to talk about what we have learned from that experiences. We use asphalt materials every day, even without realizing it. Most of the pavement of the infrastructure that support our social and economical development are constructed using this type of material. Indeed, more than a half of the urbanized surface in developed countries is covered by asphalt. So it can be considered as one of the most important construction materials. And because of this fact, it has a great impact in our life. Most of the goods that we consume arrive to us over asphalt. Our countries invest every year a lot of money on this material. It has a great impact in our safety every day and also in our environment. So for us, it is crucial that asphalt material offer a good performance and also a good durability. Nonetheless, the ideal asphalt material does not exist. So it must be designed based on the type of load and environmental condition to be supported. To design asphalt material is the process of determining the type of material to be used and the optimum combination of this material. So basically, it can be divided in 4 different steps. To determine the type of aggregate and mineral skeleton to be used, to define the type and content of binder, to decide if we are going to use any additive under dosage, and finally, to determine the thickness of the layer to be used. It seems a simple task, but indeed it is not, because all these variables are related, and the relationship between them is not univocal and depend on many external factors. So, several years ago, when I started to study asphalt material, I wondered if there were any gap that prevent us from designing more durable asphalt material during the design stage. And the first thing that I noticed is that most of the loads supported by asphalt material during the service life are cyclical loads that after a certain number of repetitions cause their failure. Nonetheless, most of the tests used during the design stage apply monotonical loading. These tests are useful, but sometimes they are not sensitive enough to justify small increment in the binder content or the use or not of additives and modifiers. Rarely, cyclic loading tests are used during the design stage, and due to the time and the material consumed on this type of test, they are usually limited to validate a binder content already selected with monotonic tests. In addition, most of the tests used when designing asphalt material do not apply similar complex effort than those supported by this material during their service life. Most of the tests apply single efforts such as bending, tensile, shear, but not a complex state like shear plus bending or plus tensile as occur in asphalt material. Materials have not a unidirectional propagation of damage. When you apply a load over a material, the material will respond with mechanical change in the same direction of the load, but also in the normal direction. And because of this fact, damage propagates randomly and aleatorily inside the volume of the material. Nonetheless, most of the tests measure the change produced in the material just in one direction. And because of this fact, it is not possible to have an accurate measurement of the propagation of the damage. These aspects reduce the repeatability of the test and also reduce its sensitivity to the change on the material design. Other aspect that prevents us from having an accurate measurement of the propagation of the damage in asphalt material is that most of the analysis of the result use linear elastic mechanics. Asphalt material are far away from behave like a linear elastic mechanic. And in the end, I noticed that during their service life, asphalt materials do not work individually. They form a part of a complete structure. And the property of the other material being in the structure has a great influence in the final mechanical response of asphalt material. Most of traditional tests evaluates asphalt material as an individual material without taking into account the effect of the supporting structure. So when I finish this analysis, I wonder how can this gap be filled? Or in another way, how can this process can be easily improved? And I decided to develop the University of Granada fatigue asphalt cracking test. This is an instrument. This is a low-cost instrument with reduced dimension that can be adapted to any laboratory dynamic press that has a low material consumption. The test is carried out inside a climatic chamber where the environmental condition of the material can be changed. And it can reproduce similar complex effort than those produced in asphalt material during their service life. For this purpose, this test is composed of a base where two supports are placed, and over that support there are two places where the specimen is fixed. Under that place there are two elastic elements that when we applied a load, like a traffic load, allow for the bending of the asphalt material, and after that one of the support is fixed and the other one can move. So when the bending moment is reached, after that the sliding support moves, inducing a shear and tensile effort inside the volume of the material that we are evaluating. We have a recovery spring that simulates the foundation layers in the material. So basically, this is an overview of the University of Granada fatigue asphalt cracking test. Here you can see the elastic elements, the recovery spring, and the sliding support. The test can have different type of configuration by varying the distances between the plate. So we can simulate different type of deterioration under the asphalt layer, like crack, pre-crack, dilatation joint, pothole, etc. In addition, the presence of the recovery spring allows us for simulating different type of base and foundation material. So when we apply loads in our material as occurring raw, we are going to have deformation on it. But if the characteristic of the foundation change, for example, we have a weaker base or a weakened foundation layer, the deformation becomes bigger. So the only thing that we need to do is to change the stiffness of the spring, and we can reduce and simulate different types of bases. This type of test also help us, allows us to evaluate complete pavement layer or several layers of the pavement, evaluating the efficiency of the adherence between layers, and also the use of geotextile or other reinforcing places over the two layers of the asphalt. In addition, it offers very valuable information for improvement asphalt material design in a structural way, because we record every horizontal and vertical movement produced on that volume due to different type of load and base characteristic. For this purpose, the UGR FACT is provided with 4 LVDT. 2 of them are going to measure the displacement produced in the vertical direction, and the other 2 measure the displacement produced in the volume in the horizontal direction, 2 of them in each side of the specimen. So this configuration allows us the evaluation of the material inside a volume, avoiding its randomness and the 3-dimensional dispersion of the damage produced in the material during the test. Taking that information, what we do is record every relative displacement produced in the asphalt material in both directions, in the vertical and in the horizontal one. These displacements are typically recorded in all types of tests and is related to the consistency of the material or the damage state. But in addition, we also record every single permanent displacement produced in the material, which are related with the change produced in the geometry of that volume. By combining both information, we can obtain a control of the volumetric change produced on the viscoelastic response of the volume, but also the control of the volumetric change produced in the geometry of the material due to the permanent deformation. So, as I told you, combining these 2 parameters, we can have an accurate measurement of the real mechanical response of this material. For this purpose, we put in the x-axis the dissipated energy, and on the y-axis the change in the geometry. So when we obtain big change in the geometry of the volume, that corresponds at the beginning of the test to plastic deformation or other viscoelastic phenomena, and at the end of the test to macro cracks. And when we obtain low values of this change on the geometry of the volume, we are going to have a stage that microcracks, small variation of geometry, are producing inside the volume. Analyzing the dissipated energy, we can observe that initial dissipated energy is related to the viscoelastic response of the material under that condition that we are testing. Low values of the initial dissipated energy are related to a more elastic response, while high values are related to a more viscous behavior of this material. During the test, if the values of dissipated energy go to the left side, to the initial dissipated energy, we can observe that the material is suffering a strain hardening processes due to the plastic deformation. If they go to the right, to the initial dissipated energy, that means that the material is suffering damage on that. So basically, at the beginning of the test, in all tests, we can observe at the beginning a considerable change in the geometry of the material. Consider that this is a logarithmic scale, so we are going a considerable change in the geometry of the material, but the dissipated energy remains almost constant. So that means that there's no damage in my material, and the deformation that we are controlling are only due to plastic deformation or other viscoelastic phenomena such as heating or other. Then we are going to have a second part where changing the geometry becomes very low and the dissipated energy starts to grow. So that means that we are in the damage initiation phase. And in the end, in the last part, geometrical change starts to grow again, and also dissipated energy grows drastically. So that means that we have damage propagation stage. If we combine this information with the number of low cycles applied that produce it, we can identify many different properties inside our material. For example, the deformation susceptibility, because we have the number of cycles that does not cause a real damage on my material, just only deformation. But also we can distinguish between the different phases of the propagation of real damage, the micro and the macro process. Taking that information, we can define the mean damage parameter that is a summatory of the increment of the dissipated energy produced in the material during the test, divided by the number of load cycles that need to it. And varying the temperature condition or the load condition that we are using to evaluate the material, we can obtain fatigue loads that help us to design more accurate asphalt material. So basically, with this test, we can easily identify each of the stages of the mechanical performance of the material and act to them to identify the benefits produced by additive or odd bitumen modifier in each of those stages. The Laboratory of Construction Engineering of the University of Granada have used this tool during the last 8 years successfully in fundamental research, but also in the design of real asphalt material in pavement, from urban solution to conventional road, but also we have used it in highways. And because of that, I will show you the potential of this tool in the different stages. Starting by the beginning, by the design stage in the laboratory, I will show you the sensitivity of this test to the design variable, such as the density, voids, binder content, binder type of the use of additives. For that purpose, I will show you an example with a BBTM mixture, which it is a common mixture used in surface layer in highways in Spain. And a Spanish standard gives that recommendation to design it. It says that the compaction energy must be 50 loads per side in the Marshall compactor. The minimal void content must be 4. The minimal binder content must be 5.2. And the binder to be used should be a polymer modified binder 45, 80, 65. Okay, if we start to design a material under that criteria, we can apply 50 blows per side, and we are going to obtain a material that has around 6%, for example, that is accomplished with the criteria, and with a density and a resistance in fatigue asphalt cracking test of around 3,000 cycles. That's okay. It's okay, but if we change the compaction energy used in the material, it is observed that as the density increases, the mechanical resistance of the material increases. That means that not all asphalt material, not all additives, not all will have the same compaction energy. So we need to focus on trying to obtain the maximum density by respecting the number of voids of the material. So just changing at 2% the void content of the asphalt material, we can increase by a 70% their service life. Secondly, dealing with the binder and the type of binder content and the type of bitumen to be used, we can observe that the minimum binder content is around 5.2. By slightly increasing that binder content, we can double the fatigue life of that material, and increasing it less than 1%, we can reach like 80% increment of the service life of the material. In addition, many binders can accomplish with that standards of polymer modified binder. But if you take two different types of this binder and you pick on a more elastic one, you can notice that you can have a slightly considerable increment on the fatigue life of this material, especially when the loads are higher. And in the end, additives are usually not advised when you are designing asphalt material because it increases the cost and all that. But definitely, if you use additives in the material like fibers, you can increase drastically its mechanical performance, you can increase their service life, and also if you use other type of additives like waxes or surfactant material, you can reduce the material temperature of manufacture and even obtaining a good mechanical performance because the material improves its workability and it can be densified in a better way. The second part that I want to show you, or the second potential that I want to show you from this test method, is that it is very useful to determine the thickness of an overlay or the thickness of a pavement layer to be used. Right now we are going to have our road network is almost constructed, and we are going to have many activities on the rehabilitation of this type of road. We are going to have a deteriorated road, and we need for an overlay. But the typical question that we do is, what is the optimal thickness to be used, or which is the optimal material? Then what we do is to determine the type of load that the road will support, and also the characteristic of the 16th road. So we can adapt that to the University of Granada fatigue asphalt cracking test, and to test different type of materials and thicknesses at different temperatures in order to obtain the optimal thicknesses to be used in the material. For sure, if you want a durable asphalt pavement, this pavement must be as thick as possible. Nonetheless, when you compare between two types of material, you can obtain significant reduce of thicknesses when using one material or other, which allows us for have another criteria to select the optimal material to be used during the rehabilitation. And finally, another of the interesting application of this test is the monitoring of the performance of the asphalt layer constructed in real road. For that purpose, what we organize is different campaign of course. We start different course at different season from the road, and we evaluate it in the fatigue asphalt cracking test. We determine the fatigue life after the construction, and then after different period, like in an example, after 4 years, and we obtain the different reduction of the fatigue life. Setting that in a graph of service life in year and pavement performance measured through the cycle to failure of the course, we can determine the evolution of the mechanical performance of that real road in order to determine when is the optimal period to act. At the end, and as a conclusion, if you want a recipe to design more durable asphalt material, I should say that it does not exist. Does not exist a global recipe to be applied. Nonetheless, based on our experience, I can give to you some recommendations. The first one is to select an asphalt binder as elastic as you can, with a high modulus and a high rate of elastic recovery. In addition, the binder content should be high enough in order to avoid a brittle performance at low temperature and to a brittle performance after aging. With this criteria, we can have small deformation even at high temperature and low cracking risk even at low temperature and after aging. After that, we need to design it as dense as possible. For that purpose, we can use additives that improve the workability of the material, which help us to reduce the risk to plastic deformation, cracking, and environmental attacks. And finally, for sure, use pavement as thick as possible, but overall, try to not put an asphalt layer over another layer which is softer than the top one. So if we use a very stiff layer over a softer one, the problem that we can have is that the deformation in the bottom layer can be higher than in the top layer, so the deflection becomes higher. The top layer cannot go with the bottom layer, and it will crack. This phenomena also happens when we have aging. Even we have a layer, we have, when aging comes, the stiffness of the bottom part of that layer becomes much more stiff, and then we are going to appear this type of cracking. For this purpose, we can use additive in the surface layer to improve its elasticity and resistance to aging. Nonetheless, what we can do if our recommendation cannot be followed. Anyway, there's many variables that will influence. What we need to do is to use laboratory tests that can give us as much information as we can from that material and try to study it in the same way that it will perform during the service life. Before to finish my presentation, I must say that this method would not be possible without the support of the Laboratory of Construction Engineering of the University of Granada team, and also the support of the companies, association, and public administration that have supported my work. So this prestigious award also belongs to them. Thank you very much. Thank you very much, and if you have any questions, do not hesitate to do it. Thanks.
Thank you very much for this very nice and very complete presentation. We have time for a couple of questions. Do you have any question in the room? Manfred, yes?
What is the size effect?
Yeah. The size effect, it can be controlled because the specimen has not always the same size. So as you can test different type of specimen, you can test from complete pavement section till a small core taken on the road. The specimen will be manufactured based on the maximum size of aggregate. So we control it doing that. So the volume where we study, as the distance between the plates can be varied. So the volume where we study the mechanical performance of the material varies as a function of the size of the material used inside that volume.
Yes, Carmen?
Thanks for your presentation. I am not a specialist in asphalt, I am a concrete, but I have listened to some of the congresses in asphalt, and which is the relation with the other technique that you use when it's not set, the asphalt? I mean, you have like an equipment, Manfred knows well that you also obtain the viscoelastic behavior, in which you use a rotation. I think that is a rheological equipment. Have you compared or not?
Yeah, normally...
Because your figure just reminds me that problem of the viscoelastic behavior, and they study, the people on the asphalt, they study with other techniques.
Yeah, normally rheology is used for asphalt binders. Here, this material is studying asphalt mixture, the complete mixture. So, for sure, the rheology is a very interesting tool, but we are not far away from that tool, because indeed, rheology is the study of how loads affect the strain with the time. So that's the definition of rheology, and we are doing all that, because we are controlling dissipated energy and the deformation produced in different load cycles. So we take into account the number of load cycles. We have the frequency, so indeed we have time. And we use that to define our mean damage parameter. So that was one of the advantages of that damage parameter, which integrate time, number of load repetition, and change on the viscoelastic response, because we control the increment of the dissipated energy of the loading. So with just one parameter, if it is high, your material, it is susceptible to be cracked. And it is low, the material will resist.
All right, so I guess we can agree with this presentation is worth a medal, okay? So I'm just going to put the mic here. We're going to look at the camera, but here's the RILEM medal.
Oh. It was not the medal was saved.
So, congratulations.